Hello and welcome to the MOOC on optical communications. In this module, we will continue the discussion of fiber nonlinear effects. We have already seen that one can have intensity dependent refractive index, which allows us to discuss three type of nonlinearities. One is self phase modulation, the other one is cross phase modulation, and four-way mixing. Now, while that simple picture of intensity dependent refractive index was quite okay for a qualitative discussion, much elaborate models and equations have been studied over the last few years, which take into account the fiber geometry and how the modes actually propagate inside the fiber and get affected by the nonlinearities. And this equation, which is valid for pulses as well as for continuous waves, provided the pulse width of the pulses, optical pulses, is greater than about say 100 femtoseconds or so, or about 1 picosecond or so, then it is possible to capture all these nonlinear effects which we discussed in the last module, such as FWM, XPM and SPM by this particular equation. Now, in addition to these three nonlinearities, there exist other nonlinearities which are basically the which are because of the inelastic scattering that is there inside the fiber, and these nonlinear effects are the Brillouin scattering and stimulated Raman scattering. We will not consider Brillouin scattering and Raman scattering for now. We will postpone the study to later time. For now, what we will do is we will study this particular equation which allows us to model the nonlinearities that we have already discussed, and this equation is called as nonlinear Schrodinger equation. We will not derive the equation here. That derivation is something that should be postponed to a different course, an advanced course if you wish, but the implications of that equation are quite easy to discuss. So, we will begin by assuming that someone has actually derived the nonlinear Schrodinger equation. We will use that equation and discuss, in the light of that equation we will discuss self phase modulation, cross phase modulation. Four-way mixing is quite similar to it is quite a simple extension of this one, as long as we are working with simple geometry. So, we will talk about four-way mixing as well. So, what is this nonlinear Schrodinger equation that we have been talking about? Remember that in general your laser, which is producing the optical signal, will have a certain central frequency. So, let us say it has a certain central frequency of omega s. Now, if this is an ideal laser, this is what you are going to get. You are going to get in the frequency spectrum a single impulse like function, because there would be only cos of omega 0 t or sin of omega 0 t, or rather sin of omega s t or cos omega s t. In practice, a laser has a certain amount of line width, right, which we discussed in one of the earlier modules, which means that the spectrum is kind of broadened. Now, this light from the laser is usually modulated, right. So, when you want to communicate information, you communicate that by modulating the laser, and it so happens that in many other places where light is concerned, its envelope, which is how the envelope of the laser changes, that would be a function of time as well. Okay. So, if you were to call the envelope after modulation, although I am saying modulation, it is not necessary that one has to always encode information. For example, when we are considering mode locked lasers, the laser light goes from being a continuous wave, which means it has no variations with respect to time, to a pulse like behavior, and this pulse like behavior, we say that it is modulated. It does not really mean that you are transmitting information there. It simply means that the envelope is not constant, but rather changing. So, it can change in a variety of ways. Okay. So, whatever the way that it might be changing, we can represent the envelope by the amplitude function and make that amplitude function go to a function of time. It is also a function of z. Okay. So, why should it also be a function of z is something that will come when you look at the derivation of the nonlinear Schrodinger equation, something that we are not going to do that over here. So, the electric field that is coming out here after the modulation, or in general which is time varying process, can be written as e to the power j omega s t times k into z. You are familiar with this part, right. This is simply a travelling wave along the positive z direction, and k is the wave vector. In this case, we have considered k to be a scalar. However, k will be a function of omega, this function of omega is the dispersion effect. But in nonlinearities, it also turns out that the refractive index to which k is directly proportional to will also be a function of intensity, right. So, therefore, k will have a linear factor and k will have a nonlinear factor. The linear factor is the functional dependence on the frequency, while the nonlinear factor is the dependence on the intensity of the wave. Okay. So, this is the electric field that is coming out of the modulator, or in general a time varying electric field, one can imagine that one. So, this is the time varying electric field that you are looking at, and this time varying electric field has an envelope A of zt and it is propagating along the z direction. And if you look at its picture in the frequency domain, it might look something like this. So, it will be centered at the frequency fs or equivalently omega s, right, and it will have a certain spectrum. For example, if my envelope function is a Gaussian shape, right, is a Gaussian pulse, then the spectrum will also look Gaussian, right. So, this is how you would actually see the time and the frequency spectrum. And what we are concerned with, suppose you start with this envelope at z equal to 0, that is at the input of the fiber. Okay. So, this is at the input of the fiber. So, you begin here, and what you are looking at, so this is your fiber, correct. So, if what you are looking at is at a certain distance z, okay, what would be the envelope? How would the envelope look in comparison with this envelope at the input? And this equation which we talked about, called as nonlinear Schrodinger equation, actually tells us how that envelope looks at. So, it tells us that A at any z of t actually satisfies a particular equation. Okay. This is of course the nonlinear Schrodinger equation, shortened as NLSC. There are various formats of NLSC or variations of NLSC. We are concerned with the most commonly used NLSC form here. Okay. There are unidirectional NLSCs, NLSCs which are particularly applicable, which when you have to consider the time delay effects which come about because of the Raman scattering or the Brillouin scattering. One can also have a generalized NLSC, and a generalization of the NLSC itself is called as the Manakov equation. So, you have all these different equations which are kind of used or which are kind of studied under different optical phenomena. For the phenomena that we are concerned with, where the optical pulses are at about 1 picosecond width or so, this NLSC, the form which I am writing, is more than sufficient. Okay. So, we are going to consider this NLSC and see how SPM, XPM and FWM all fall out from this particular equation. So, this equation, which is the governing equation for the envelope function, okay. Governing equation for the envelope function means that the envelope is changing both along the fiber as well as in time. So, one has to look at how envelope is changing as a function of z as well as function of time. So, you would expect some terms on the right hand side to be functions of time and some terms to be there which are present, which would be functions of time was one and function of z is already there in the left hand side. So, the right hand side term should definitely consider or contain functions of time. Okay. One should also consider the intensity, because we have seen that the envelope function is going to change depending on the intensity of its own pulse, right. So, one has to also have an intensity term. Now, you might ask what happened to the loss in the fiber. Well, we are assuming in this equation loss to be 0, okay, but one can easily consider loss by making a simple transformation from envelope function A to a different envelope function which will include loss. Okay. So, we are not going to look at the loss here, we will assume that the fiber is lossless. As such, dispersion and nonlinearity are big headaches by themselves. So, we will not impose loss as an additional headache for us. Okay. So, this equation, let us get back to it, tells us how the envelope function changes as a function of z and time, and this is given by j del A of zt by del z, that must be equal to minus beta 2 by 2. I will explain these terms shortly, del square A of zt divided by del t square plus gamma magnitude A square times A of zt. We will also assume that A has been taken in such a way that it has been, the units of A has been chosen in such a way that the magnitude square is going to give me the power of the optical wave at z and varying as a function of time. So, if I were to fix z, then I will get what is the power at that particular location. Okay. So, I have chosen the amplitude in such a way that magnitude of a square will give me the power, optical power. So, this is optical power. Okay. So, this is equation which is very important for us. So, let us do the usual thing, let us box the equation and then consider the terms one by one. What is beta 2? Well, we said that k is the wave vector. In many optical communication literature, especially in the electromagnetic literature, it is common to use beta in place of k. So, this beta is the wave vector. Okay. So, instead of kz, you will have a beta z. Okay. And this beta can actually be beta can be expanded as a Taylor series approximation over the frequency range. So, one can write that beta around the frequency omega s. So, this is your frequency omega s, and here is where you are looking at beta as a function of omega. So, it will be varying in somewhat in a manner that would go like that. Okay. And you are looking at the offset between omega and omega s, and you can, if you wish, you can put the offset value as omega and then work around with that. But other than that, you can simply assume that you are looking at the value of beta of omega, which is a certain frequency away from omega s, right. And using Taylor series expansion will give us beta of omega is equal to beta at omega s, which is the value of beta at this point, plus what is the slope here, right. The slope here is del beta by del omega. Where do you have to evaluate the slope? You have to evaluate the slope at omega s and multiply this one by the offset value omega minus omega s, which is the distance between the frequency where you are considering beta and beta at the central frequency omega s, plus the second order term del square beta by del omega square at omega s, omega minus omega s whole square. There is a factor of 2 out there. Now, if you wish to keep only these 3 terms, which is normally what we do, there is a shorthand notation people have developed. The shorthand notation for this del beta by del omega at omega s is called as beta 1, and we write this as beta 1 omega s. And since this is the 0th order expansion in some sense, you can write this as beta 0 of omega s. Okay. And you also have a shorthand notation for this one, which is beta 2 omega s. Okay. So, in terms of these shorthand notations, beta at any omega, which is very close to omega s but not exactly equal to omega s, is given by beta 0 omega s plus omega minus omega s into beta 1 at omega s plus omega minus omega s whole square by 2 with beta 2 at omega s. Now, you remember we have already discussed what is beta 2. Beta 2 is the, so this is the group velocity and this is the group velocity dispersion that we have already looked at, and we have talked about group velocity dispersion in terms of a parameter known as dispersion parameter or dispersion coefficient, right. And we had related beta 2 to d. So, this is called as the dispersion coefficient and it is measured in terms of picosecond per nanometer kilometer. Okay. So, this is how beta would be expanded in general. Now, go back to the equation that we have here. So, in the equation what you see is beta 0 of omega s is missing. It is missing because when you develop the nonlinear Schrodinger equation, this beta 0 of omega s will contribute only to the fixed delay. It is kind of a delay. You start your pulse here. After some time the pulse has travelled all the way up to the fiber at certain point where you are considering the fiber, it has travelled, and beta 0 actually tells you the delay. It is a pure delay and there is nothing that is specific about that one, right. I mean, it is just a delay, so you can completely ignore that. So, you know that any information cannot travel at the speed of at the speed of infinity. So, if you start your pulse here, the center of the pulse would be arriving after a certain delay, and this is a delay that would be experienced by all frequency components. So, there is no special thing to consider here and we usually ignore this delay, okay, because it results in a fixed phase factor. The second one, the group velocity, actually means that the pulse is now travelling, the envelope is also travelling. Now, the pulse center will travel at a different velocity called as phase velocity, whereas the pulse envelope will travel at a velocity called as group velocity. and usually group velocity and phase velocity are not equal to each other except you are considering free space. However, in this case it is not free space, so they are actually not the same, group velocity being usually smaller than the phase velocity. Now, the pulse is moving. Now, instead of, see, now it is like this, you imagine the pulse to be on a train. Okay. Now, the pulse is on the train and the pulse is moving and you are standing on the platform. Now, with respect to you, both the center of the pulse as well as the envelope is moving, right. So, if you were to have a clock here and say at t equal to 0 I have launched my pulse, after say t equal to 10 the pulse would have moved a certain distance, okay, and depending on what is the group velocity and the phase velocity. Now, either you can measure the time frame from here to here, which means that you have to keep track of this beta 1 because you have to also know how the envelope is moving, or you do one thing, you simply jump onto the train. Now, you are moving along with the pulse, okay, you are moving along with the pulse, or at least you are moving along the center of the pulse. Now, you see that the skirt of the pulse, the other portions of the pulse are not exactly traveling along with you, they are traveling with a slightly different velocities. So, some portion the leading edge might be traveling faster, trailing edge might be moving slower. So, there is actually a group velocity dispersion happening, but you are sitting on the group velocity term, which means that you are moving along the center of the pulse, okay, and you are only seeing the time changes which is happening with respect to the center of the pulse. So, it is like instead of traveling instead of running along the platform or standing still on the platform and making measurements on the moving train, you jump onto the train and make the measurements. Whatever measurements that you do will be the differential measurements that you are going to do. So, difference in the time with respect to the center of the pulse, and that is precisely what this time variable t over here. In case you look at the literature, sometimes instead of using this small t, people use a capital T, okay, and they define this t as t minus I believe this must be beta 1 into z, because beta 1 or z by beta 1, I am not very sure, z by Vg, and Vg is proportional to 1 by beta 1, therefore, this is t minus beta 1 z. Okay. So, this is nothing but this is equal to t minus z by Vg. So, instead of talking about the small time t, you now talk about the difference in the time, which is like equivalent of jumping onto the train. Now, what we will do is we will assume that we have already jumped on the train. So, instead of using the capital T, we continue to use the small t, but remember in our minds that we have always been moving along the center of the pulse. Okay. If that is fine, then we can move ahead to the next portion. So, it is interesting at this point to consider this, right. You have a beta 2 which has to be accounted because the pulses would not remain in the same time slot, they are going to spread, and this spreading is the group velocity dispersion, right. So, as the pulse propagates through the fiber, it spreads out. Now, when it spreads out, you have to, that effect is because of beta 2, and that is what is captured by this particular first term over here. Notice the sign here is minus, there is nothing special about a minus sign here, but what is special is that the sign of this first term is opposite to the sign of the second term. Okay. The sign of the first term is opposite to the sign of the second term. So, if you want, you can make this plus, then you have to make this one minus, and you have to make a small change over here, does not really matter. Look at the second term. Here you have gamma, which we have discussed. If we have not discussed, gamma is the nonlinear coefficient. We have discussed N2 as the nonlinear coefficient, or rather the nonlinear refractive index. This gamma is related to N2, but it also takes into account the effective area of the fiber. So, if the pulses are propagating in a standard single mode fiber, you have a certain effective area. If instead they are propagating in a dispersion compensating fiber with a different refractive index profile and a different geometry aspects of a different core radius, different cladding radius, then that effective area is also taken into account. Okay. So, this gamma is a nonlinear coefficient which is usually measured in per watt kilometer. Okay. And A we have already discussed is the envelope. So, this is what the nonlinear Schrodinger equation is. We have described every term that is over here. Now, what we do is we quickly move on to one very simple case. Okay. This is just to reconfirm that the nonlinear Schrodinger equation is making sense to us. So, what we will assume is that there is no nonlinearity in the fiber. So, no nonlinearity implies we set gamma equal to 0, right. So, although the equation is supposed to be used for nonlinear effects, one can always set gamma equal to 0 to examine whether the equation would be consistent with our earlier ideas of dispersion. What is our earlier idea of dispersion? Suppose you take a Gaussian pulse whose FWHM is some t0, then we know that the Gaussian pulse actually spreads out. Its amplitude drops and the pulse will spread out with the pulse width at after a certain length z being somewhat given by t0 square beta 2 L whole square if I am not wrong. So, something like this. Okay, we had derived this result earlier, right. So, as the length increases, the pulse width also increases. We have derived this result in one of the earlier modules. So, you can just look at what is the exact expression there. But the point is the pulse will spread and of course, its amplitude will also drop, but whether this phenomenon of pulse spreading is predicted by the nonlinear Schrodinger equation or is it taken into account by the nonlinear Schrodinger equation is what we want to consider. Okay. To do that, let us so we have set gamma equal to 0 and let us look at what happens to the Schrodinger equation. So, nonlinear Schrodinger equation. So, you have j del A of z del z is equal to minus beta 2 by 2 del square A by this A is also a function of z and t. So, this is del square A by del t square, correct. Gamma is equal to 0. Now, how can I solve this equation? On one hand I have z, on one hand I have time. Now, I am not going to give you a lecture on partial differential equation, but one method which you might be familiar with your studies on partial differential equation is to actually take the Fourier transform. So, on both sides you take the Fourier transform with respect to what? With respect to time, not with respect to z, with respect to time. So, when you take the Fourier transform, we know that del square by del t square will become j omega whole square, which is basically minus omega square, correct, and A of z and t becomes, after taking the Fourier transform, sum A bar, which is the Fourier transform representation of z and omega. So, at a particular z, right, you take the Fourier transform, it becomes A of z and omega. Put that into the equation here. So, what you get is j del A of z omega divided by del z. So, there is no change here with respect to the variable z here, but things become interesting here. Now, you get minus omega square beta 2 by 2, but again you have to remember that this omega is actually the offset frequency. Okay. It is actually the frequency difference between the carrier or the central frequency omega s and the frequency that you are looking at. Okay. So, it is the offset frequency as we discussed that you have to look at. Here I have A of z omega. Now, this equation is a first order differential equation which is nicely in the so called variable separable form. So, I can integrate the equation, and so before doing that maybe I can push this j to the right hand side. So, when I push j to the right hand side, this becomes 1 by j and j and goes and becomes plus j over here, correct, because 1 by, so, or you can multiply by minus j on both sides. So, here it would be plus 1, so here it would be plus j times something. So, what I get here is d A of z omega divided by A of z omega is equal to j omega square beta 2 by 2 times dz. Integrate on both sides and remember that integral of dA by A is nothing but log of A, and you will have this fellow being j omega square beta 2 by 2 into z. Okay. Now, this fellow would be log of A z of omega, this must be equal to this fellow plus some constant of integration c. Okay. You can now take the constant of integration to be something like A of 0 comma omega, because the variable is with respect to z, and rearrange the equation to be A of z omega is equal to, or rather you take this as log of this fellow, right. So, you can write this as A of 0 omega e to the power j omega square beta 2 z by 2. Now, this equation at this point may not make too much sense to you. Let me explain the equation. What has actually happened here is that we started off with the fiber. At the fiber input, the pulse envelope was given to us. The pulse envelope is A of 0 t, 0 being at the fiber input what is the pulse envelope. Okay. So, A of 0 t. Now, you propagate this pulse through the fiber of a certain length L, that is at z equal to L. Okay. How do you propagate this? What you have to do is you have to take the Fourier transform of this equation. The Fourier transform of the pulse envelope at the fiber input will be given by A of 0 omega, and now you propagate this A of 0 omega at a distance of z equal to L, which would be A at z equal to L comma omega, being related to A at 0 omega by multiplying it with a factor of omega square beta to L by 2. Now, you are not interested in the frequency spectrum, are you? You are interested in the time domain variation, and to get to the time domain thing you have to take the inverse Fourier transform here. So, if you take the inverse Fourier transform you get A of L comma t, which is exactly what you are looking for. Let us very quickly apply this formula, okay, kind of a formula that we have derived for propagation when there is no nonlinearity, to the familiar case of Gaussian pulse. The Gaussian pulse will be at 0 of t can be written as e to the power minus t square by 2 t 0 square, where t 0 is of course the FWHM of the pulse, or rather t 0 is proportional to the FWHM of the pulse. What is the spectrum of this one, or the Fourier transform of this, which is A of 0 omega is e to the power minus omega square t 0 square by 4. Okay. Now, what would be the Fourier transform at L, which is at z equal to L? This would be equal to e power minus omega square t 0 square by 4. Please note that I have not multiplied this one with a certain constant. I have to actually multiply this one with a certain constant here, right, because I have taken the amplitude here as 1. I have to multiply this one by a certain constant, which I have not done, okay, and this constant will be a function of t 0, or rather 1 by t 0. Okay. So, I have not done that one because I am not interested in showing you the amplitude changes, I am interested in showing you the pulse change in the time domain. Now, you have got the, so what is the first step? This is the first step. You start with the pulse envelope at z equal to 0, which is at the input of the fiber. The second step is to take the Fourier transform. The third step is to propagate this Fourier transform through the fiber of length L, and the Fourier transform would be obtained by multiplying it by e power j omega square beta 2 L divided by 2. Now, what would be the fourth step? Fourth step would be to take the inverse Fourier transform. Now, before taking that, let us simply rearrange the equation here. So, this right side can be rearranged as e power minus omega square by 4. So, you have t 0 square plus 2 j 2 omega square beta 2 into L. Okay. Now, this fellow can be written as some t z square or t L square, which is the pulse here, right. So, you can write this as t z square or t p square, let us say. It is the pulse after propagating through a distance L. What would be the inverse Fourier transform of this? Clearly, the inverse Fourier transform of this one will be some e power minus half t square divided by t p square, right. So, the new pulse width t p will be given by square root of t 0 square plus j 2 omega square beta 2 L, right. Of course, you have to first convert this equation, or rather let us write simply as t p square. So, you have to convert this equation into its real and imaginary or the polar form. So, when you write this equation into polar form, there will be magnitude of t p over here, and then there would be an angle of t p. This angle of t p will be function or is given by this omega square is not here in this equation, because we had to taken omega square as a common factor, right. So, when you take a look at this one, this would be the, so there is actually in addition to pulse change, there is also what is called as chirping in the pulse, right, and this chirping is given by this particular phenomenon, right. So, this is exactly what is happening. There is an extra phase that is coming in, but the pulse width has actually increased. Do you agree that the pulse width has increased? Yes, as if beta 2 is positive, which is quite common for the pulses propagating in the fiber in the normal dispersion regime, then beta 2 is positive, then positive beta 2, L is also positive, and when you take the magnitude of this particular term, it is going to be larger than t 0 square, and hence what you get is a pulse which is spread in time. So, we will stop here and continue the discussion of the nonlinear Schrodinger equation in the next module. Thank you very much.